October 25, 1944. The waters east of Samar Island in the Philippines, 6:30 in the morning. Ensign Hans Jensen was making a routine patrol sweep in his TBM Avenger torpedo bomber, launched from the escort carrier USS Kadashan Bay. The sun had barely crested the horizon when anti-aircraft fire suddenly exploded around his aircraft. His radio crackled to life moments later as Ensign William Brooks from the escort carrier St. Lo reported what no one wanted to hear. Enemy surface force of 4 battleships, 7 cruisers, and 11 destroyers sighted 20 miles northwest of your task group and closing in on you at 30 knots. Rear Admiral Clifton Sprague stared at the message in his flag plot aboard the USS Fanshawe Bay. His Task Unit 3, nicknamed Taffy 3, consisted of 6 escort carriers, 3 destroyers, and 4 destroyer escorts. They'd been providing air support for the Leyte Gulf landings. Now they faced the full might of the Japanese center force, 4 battleships. The Yamato herself, the largest battleship ever built, with 18-inch guns that could hurl a shell weighing as much as a small car over 25 miles, 7 cruisers, 11 destroyers, and Sprague's escort carriers? They were converted merchant ships, lightly armored, slow. Their maximum speed was 18 knots. The Japanese fleet was closing at 30. The mathematics was brutal. Sprague ordered his carriers to turn south and run. Then he gave the order that would define the next 2 hours. Launch all aircraft. Attack the enemy fleet with whatever you have. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What happened next shouldn't have been possible. Within minutes, aircraft began lifting off the flight decks of all 6 escort carriers, Wildcats, Avengers. Some were loaded with torpedoes and bombs. Others carried only depth, charges meant for hunting submarines. A few had nothing but machine gun ammunition. It didn't matter, they launched anyway. The Kitkun Bay got her aircraft airborne, while Japanese shells were already bracketing the ship, geysers of water erupting around her hull. The Gambier Bay, the White Plains, the Fanshawe Bay, all of them emptying their flight decks as fast as crews could move. The conventional wisdom in October 1944 said this was impossible. Escort carriers were slow, limited, meant for convoy protection and ferrying aircraft, not combat operations against battleships. Their short flight decks, about 400 feet of usable space, meant aircraft could barely get airborne with any meaningful weapons load. Yet here they were, launching strike after strike against the most powerful surface fleet Japan had left. The secret wasn't courage alone, though there was plenty of that. The secret was a piece of engineering that the Navy's own experts had initially rejected as unnecessary. The hydraulic catapult system that could accelerate a 9,500-pound aircraft from 0 to 61 knots in 73 feet. If you're finding this story as fascinating as we did researching it, take a quick second to hit that like button and share this with someone who loves military history. A system that had been developed by a company in York, Pennsylvania, better known for manufacturing water turbines. A system that transformed escort carriers from second-rate convoy escorts into combat-capable warships that could launch fully loaded strike aircraft in conditions that would have grounded them otherwise. The secret was a piece of engineering that the Navy's own experts had initially rejected as unnecessary. A hydraulic catapult system that could accelerate a 9,500-pound aircraft from 0 to 61 knots in 73 feet. A system that had been developed by a company in York, Pennsylvania, better known for manufacturing water turbines. A system that transformed escort carriers from second-rate convoy escorts into combat-capable warships that could launch fully loaded strike aircraft in conditions that would have grounded them otherwise. This is the story of how that system came to be, how it was almost never built, and how its existence changed the outcome of World War II in ways most historians never acknowledge. Let's go back to December 1940, because that's when this story really begins. Admiral William Halsey sat in his office at the Navy Department in Washington, composing a letter he'd been mentally writing for weeks. Halsey commanded the aircraft battle force, and he had a problem that kept him awake at night. The United States Navy had exactly 6 aircraft carriers, 6. Against the combined might of Germany and Japan, should America enter the war everyone knew was coming. The letter he sent to Chief of Naval Operations Harold Stark on December 13th was blunt. If the United States entered the European war, all 6 fleet carriers would need immediate deployment. That would leave 0 carriers for training new pilots, 0 carriers for ferrying aircraft to overseas bases, 0 carriers for the 100 other missions that were going to be essential in a global war. Halsey proposed converting suitable merchant vessels into auxiliary aircraft carriers, not full-size fleet carriers. Those took 3 years to build from keel to commissioning. Something smaller, cheaper, faster to produce. The Navy could crank them out by the dozens while the big fleet carriers were still on the drawing boards. The Navy's reaction was less than enthusiastic. Converting merchant ships into carriers, the idea sounded desperate. Makeshift. These wouldn't be real warships, they'd be floating compromises. Half the length of a fleet carrier, a third of the displacement. Slower, more lightly armed, carrying maybe 25 or 30 aircraft instead of 90. But desperation has a way of making compromises acceptable. 7 days after Halsey sent his letter, President Franklin Roosevelt weighed in. He wanted those escort carriers, and he wanted them now. The conversion program began almost immediately. The first was USS Long Island, converted from the merchant ship Mormac. Commissioned in June 1941, she had a flush flight deck extending 362 feet, a catapult to launch planes off her port bow, and a single elevator. She was designed to carry 16 aircraft. The Navy classified her as AVG-1, Auxiliary Aircraft Escort Vessel. The name alone suggested low expectations. The problem with Long Island and the early escort carriers that followed became apparent during the first operational tests. The flight deck was short, very short. A standard fleet carrier had over 800 feet of deck to work with. Escort carriers had maybe 400 feet of usable space, and that was if you kept every other aircraft below in the hangar deck. For small, light aircraft, like the OS-2 U Kingfisher floatplane or the F-4F Wildcat fighter, this wasn't necessarily catastrophic. In ideal conditions, with the ship steaming at full speed into a strong headwind, these aircraft could manage a deck takeoff. The relative wind over the deck, the ship's 18-knot speed plus whatever natural wind was blowing, would sometimes provide enough lift. But the TBF Avenger torpedo bomber, that was a different story. The Avenger was the escort carrier's heavy hitter, a 3-man bomber with a 1,000-mile range, capable of carrying 2,000 pounds of bombs or depth charges in its bomb bay, or a Mark 13 torpedo slung underneath. This aircraft was essential for anti-submarine warfare, for striking enemy shipping, for any offensive operation these escort carriers might undertake. And the Avenger couldn't take off from an escort carrier's deck with a full combat load, not safely, not reliably. The aircraft was simply too heavy. Under average conditions, a TBF had to leave behind its torpedo, or bomb, plus a third of its fuel, just to get airborne. That defeated the entire purpose of carrying the aircraft in the first place. Navy planners looked at this problem in early 1942 and came to an uncomfortable conclusion. Without a way to launch fully loaded aircraft, escort carriers would be relegated to second-tier missions. Ferrying planes, providing minimal air cover for slow convoys, training duties. They wouldn't be combat platforms, they'd be floating parking lots. The solution existed, in theory. Catapults, mechanical systems that could accelerate an aircraft to flying speed before it reached the end of the flight deck. The technology wasn't new. The Navy had been experimenting with catapults since the 1920s, using them on battleships and cruisers to launch seaplanes for reconnaissance. Even some fleet carriers had catapults installed. But there was a critical difference. Fleet carriers rarely used their catapults. They didn't need to. With 800 feet of deck and the ability to steam at 30 knots, a fleet carrier could launch most of its aircraft conventionally. Catapults were for special circumstances, experimental purposes, edge cases. Escort carriers would need catapults for every single launch, 100% of the time, and in 1942, Nobody had ever built a catapult system designed for that kind of continuous, intensive use under combat conditions. The engineering challenges were substantial. A catapult for an escort carrier needed to accelerate a 9,000-pound aircraft to at least 60 knots in less than 75 feet. It needed to do this hundreds of times without breaking down. It needed to work in rough seas, with the ship rolling and pitching. It needed to be reliable enough that pilots would trust their lives to it launch after launch. The hydraulic pneumatic systems used on cruisers wouldn't cut it. Those were designed for launching much lighter seaplanes. The forces involved were completely different. Scaling them up for a fully loaded Avenger would require a complete redesign. The Bureau of Aeronautics started looking for contractors who could develop such a system. They needed companies with experience in hydraulic systems, companies that understood high-pressure fluid dynamics, companies that could manufacture precision mechanical components under wartime conditions when materials and skilled labor were already stretched thin. One name kept coming up in discussions. The S. Morgan Smith Company of York, Pennsylvania. Smith was an odd choice in some ways. They weren't a defense contractor. They didn't make weapons. They made water turbines, massive hydraulic turbines for hydroelectric dams and power plants. The company had been around since the 1860s, building some of the largest and most powerful hydraulic machinery in North America. But that hydraulic expertise was exactly what the Navy needed. Smith's engineers understood how to move enormous forces through fluid systems. They understood pressure dynamics, valve timing, the metallurgy required for components that would experience repeated stress cycles, the skills required to build a turbine that could harness thousands of horsepower from falling water weren't so different from the skills needed to build a catapult that could fling a 4.5-ton aircraft off a ship's deck. The contract went to S. Morgan Smith in early 1942. The specifications were demanding. The catapult needed to launch a 9,500-pound aircraft to 61 knots in 73 feet. It needed to use hydraulic fluid rather than explosive charges, which were dangerous in combat. It needed to be compact enough to fit in the limited space below an escort carrier's flight deck, and it needed to be ready for installation in ships that were already under construction. Lead engineer on the project was a man whose name has been largely lost to history. We know he worked for Smith. We know he assembled a team of hydraulic specialists, metallurgists, and mechanical engineers. We know they worked in isolated facilities, compartmentalized for security. But the individual who conceived the final design, who solved the problems that made the H-4 catapult possible, remains anonymous in the historical record. Let's call him by the role he filled, the chief engineer, because that's how such men were typically known. The chief engineer's first challenge was understanding exactly what forces were involved. Accelerating 9,500 pounds from 0 to 61 knots means imparting a specific amount of kinetic energy in a very short time and distance. The math is straightforward. The engineering is anything but. A hydraulic system works by incompressible fluid transmitting force through a sealed chamber. Pump fluid into one end of a cylinder, and a piston at the other end moves. Increase the pressure, and the piston moves with more force. The beauty of hydraulics is mechanical advantage. A relatively small pump can generate enormous forces at the output end, but there's a catch. The system has to be perfectly sealed. Any leak means pressure loss. Any air bubble in the fluid means compressibility, which wastes energy and creates unpredictable behavior. And when you're dealing with pressures high enough to throw an aircraft off a ship, even small problems become catastrophic failures. The chief engineer's design used compressed air as the primary energy source, with hydraulic fluid as the transmission medium. Large steel bottles stored compressed air at pressures around 1,500 pounds per square inch. When a launch was ordered, valves would open, releasing compressed air into a hydraulic cylinder. The air pressure would drive a piston, which was connected through a system of pulleys and wire rope to a shuttle on the flight deck. The shuttle, a metal carriage that ran along a slot in the deck, would attach to the aircraft's landing gear or to a bridle, basically a wire harness that hooked to the plane. When the catapult fired, the shuttle would accelerate down the slot, dragging the aircraft along until it reached flying speed. At the end of the stroke, the shuttle would stop abruptly using a braking system, while the aircraft would continue forward and hopefully into the air. This description makes it sound simple. It wasn't. Every component had to be engineered to perfection. The wire rope connecting the piston to the shuttle had to withstand forces that would snap lesser materials like thread. The pulleys had to be machined to tolerances measured in thousandths of an inch, or friction would waste energy and cause premature wear. The valves controlling air and hydraulic fluid flow had to open and close at precisely the right moments, or the catapult would either fail to generate enough force or would tear the aircraft apart with excessive acceleration. Then there was the retraction system. After each launch, the shuttle had to return to the starting position for the next aircraft. This required another set of cables, additional hydraulic systems, and careful timing so the shuttle could be back in position within about 2 minutes. Escort carriers needed to launch aircraft quickly, particularly in combat. A slow catapult would create bottlenecks, aircraft stacking up, waiting their turn, vulnerable to enemy fire while sitting on deck. The metallurgy was equally critical. Components would experience millions of stress cycles. A catapult installed on an escort carrier in 1943 might make 1,500 launches before the war ended. Each launch subjected the machinery to shock loads, vibration, thermal cycling as hydraulic fluid heated up during operation. Standard carbon steel would develop fatigue cracks, welds would fail, seals would leak. The engineering team tested different steel alloys. They ran destructive tests, operating prototype components until they failed, then analyzing the failure modes. They experimented with different hydraulic fluids, looking for formulations that wouldn't catch fire if a leak occurred near hot machinery, but that would still function properly at the high pressures involved. The pressure calculations alone took weeks to finalize. The chief engineer knew that compressed air at 1,500 psi could store enormous energy, but releasing it too quickly would create shock waves that could damage the aircraft's structure. Release it too slowly, and the acceleration would be insufficient. The valve timing had to be perfect. He worked with a team of valve specialists from the company's hydraulic turbine division. These men understood flow dynamics in ways that most engineers didn't. When water flows through a turbine, the timing of gate openings determines efficiency. Open the gates too fast, and you get turbulence. Too slow, and you waste potential energy. The same principles applied to compressed air flowing into a hydraulic cylinder. They built a test rig that could measure pressure changes in milliseconds. A series of gauges mounted along the hydraulic cylinder recorded pressure at different points during a simulated launch. The early tests showed wild fluctuations. Pressure would spike at one point, creating a hammer blow effect. Then it would drop suddenly, causing a lull in acceleration. An aircraft experiencing these forces would be shaken apart. The solution involved a cascade valve system. Instead of one large valve opening all at once, a series of smaller valves opened in sequence, each one timed to smooth out the pressure curve. The first valve would crack open, allowing initial pressure build-up. A tenth of a second later, the second valve would open, adding more flow, then the third, then the fourth. By the time all valves were open, the pressure curve was smooth enough that an aircraft could tolerate it. But this created a new problem. Each valve required its own control mechanism. Each control mechanism had to be synchronized with the others to within thousandths of a second. In 1942, electronic controls didn't exist in any practical form. Everything had to be purely mechanical. The engineering team designed a cam system. A rotating shaft with precisely machined cams would trigger each valve in sequence. The shaft was connected to the main hydraulic piston, so as the piston moved, it would automatically trigger the valves at exactly the right moments. This was clockwork precision, applied to a system generating thousands of horsepower. The machining tolerances were absurd. The cams had to be accurate to within 5,000ths of an inch. Any deviation and the valve timing would be off, which would throw off the entire pressure curve. Smith's machine shop had the precision equipment needed, barely. They were used to machining turbine runners where tolerances mattered. But this was even more demanding because the system had to work while experiencing violent acceleration forces. Testing revealed another issue nobody had anticipated. When the shuttle reached the end of its stroke and stopped abruptly, the kinetic energy had to go somewhere. The braking system absorbed most of it, but some energy reflected back through the cables as vibration. This vibration would travel back down to the hydraulic cylinder and cause the pressure gauges to fluctuate wildly for several seconds after each launch. That wouldn't have been a problem except for one thing. Escort carriers needed to launch aircraft quickly. The goal was 2 minutes between launches. If the hydraulic system was still vibrating and settling from the previous launch, trying to launch another aircraft during that period could cause unpredictable results. The chief engineer added dampers to the cable system. These were mechanical shock absorbers positioned at key points along the cable run. When vibration started traveling through the cables, the dampers would absorb the energy and dissipate it as heat. This reduced the settling time from 15 seconds down to about 5, which was acceptable. The cables themselves were another engineering challenge. They needed to be strong enough to pull a 9,500-pound aircraft without braking, but flexible enough to run over the pulley system without fatiguing. Standard aircraft cable wouldn't work. It was too light. Ships' mooring cable was too stiff. The team had to work with wire rope manufacturers to develop a custom specification. The cables they settled on used a 19-wire construction with a fiber core. Each individual wire was made from high-tensile steel with a tensile strength of 280,000 pounds per square inch. The fiber core, soaked in lubricant, reduced internal friction and improved flexibility. The finished cable had a braking strength of nearly 60,000 pounds, which gave them a safety factor of about 6-to-1 under maximum load. Even so, cables were considered consumable items. After a certain number of launches, they would be replaced as a precaution. The Navy established maintenance schedules based on the testing data. Every 500 launches, the cables would be inspected for wear. Every 1,000 launches, they would be replaced regardless of visible condition. This seemed wasteful until you considered that a cable failure during launch could kill the pilot and destroy a $1 million aircraft. The shuttle design went through 7 iterations before they got it right. The shuttle was the component that was actually attached to the aircraft and rode along the flight deck slot during launch. It needed to accelerate smoothly, transfer force to the aircraft without damaging it, then stop suddenly at the end of the stroke without bouncing back. The first prototype shattered during testing. The forces involved were simply too high for the cast iron construction. The second prototype, made from forged steel, held together but deformed after repeated launches. The third prototype worked for about 50 launches before stress cracks appeared in the mounting points. By the 4th iteration, the engineering team understood the problem. The shuttle wasn't just experiencing tension from pulling the aircraft forward. It was also experiencing torsional stress from the aircraft, trying to yaw left or right, bending stress from the aircraft's weight, and impact stress every time it hit the end stop. The shuttle had to resist all of these forces simultaneously. They redesigned it using a box beam construction, 4 steel plates welded together to form a hollow rectangular section, with internal ribs for reinforcement. This distributed stress more evenly and eliminated the failure points. The 6th prototype lasted 300 launches before showing any wear. The 7th and final design incorporated minor refinements and became the production standard. The holdback fitting was equally critical. This was the device that attached the aircraft to the deck and kept it stationary while the catapult built up pressure. When the catapult fired, the holdback had to release at exactly the right moment. Too early, and the aircraft would start moving before full pressure was reached, resulting in insufficient launch speed. Too late, and the excessive force could damage the aircraft's structure. The Navy used a tension bar system. A steel bar of precisely calculated diameter would connect the aircraft to the deck. As the catapult built pressure and the shuttle tried to move forward, tension would build in this bar. When the tension reached a specific level, the bar would shear cleanly, releasing the aircraft. The shear point was calibrated based on the aircraft's weight and the desired launch speed. This meant that every aircraft type needed its own holdback bar specification. An F-4F Wildcat, weighing 6,000 pounds, would use a different bar than a TBF Avenger weighing 9,400 pounds. The deck crews had to know which bar to use for which aircraft, and they had to install it correctly every single time. A mistake could be fatal. The S. Morgan Smith team developed training materials for Navy personnel. Detailed manuals explaining how the catapult worked, how to operate it, how to perform routine maintenance, and how to diagnose problems. They created cutaway diagrams showing every component. They wrote troubleshooting guides that walked through common failure modes and their solutions. But manuals only went so far. The Navy needed hands-on training. Smith's engineers worked with the Naval Aircraft Factory in Philadelphia to set up training programs. Navy personnel would spend 2 weeks at the facility, learning catapult operation from the ground up. They would practice on training rigs that simulated the actual equipment on escort carriers. They would deliberately induce failures and practice fixing them under time pressure. The first graduating class of catapult officers and crews reported to escort carriers in early 1943. These men were the specialists who would operate the most critical piece of equipment on the ship. The catapult officer was typically a warrant officer or junior lieutenant, someone with mechanical aptitude and the ability to make split-second decisions under pressure. His crew consisted of 6 to 8 enlisted men who handled the physical work of hooking up aircraft, operating valves, and performing between-launch checks. These crews developed their own techniques and shortcuts that weren't in the official manuals. They learned that you could tell if the hydraulic pressure was right, just by listening to the sound the system made when building up. They figured out that certain weather conditions required slightly different valve timing. They discovered that the cables would last longer if you rotated which pulley position they ran through, evening out the wear. This practical knowledge was passed down from experienced crews to new personnel. It became part of the oral tradition of escort carrier operations, the kind of knowledge that never makes it into official documents, but that makes the difference between a system that works adequately and one that works superbly. By mid-1942, they had a working prototype. It was installed in a test facility that replicated an escort carrier's flight deck. Weighted sleds representing aircraft were attached to the shuttle and launched repeatedly. The engineers measured acceleration, timing, and stress on components. They simulated rough seas by making the test platform rock and pitch. They ran launches in rain, in heat, in cold, documenting how environmental conditions affected performance. The first full-scale test with an actual aircraft came in late 1942. An F-4F Wildcat, fully fueled and armed, was hooked to the catapult. The pilot ran through his pre-launch checklist. The catapult officer, the crew member responsible for operating the system, checked pressure gauges, confirmed the shuttle was locked in position, verified the holdback fitting that would keep the aircraft stationary while the catapult built up pressure. The officer gave the signal. Valves opened. Compressed air slammed into the hydraulic cylinder. The piston moved. Cables went taut. The shuttle accelerated. The Wildcat went from 0 to flying speed in just over 2 seconds, travelling 73 feet before the pilot felt the nose lift. The aircraft climbed away cleanly. The catapult had worked exactly as designed. Then they tried it with a TBF Avenger. Fully loaded. Torpedo underneath. Full fuel tanks. The aircraft weighed 9,400 pounds, just shy of the catapult's rated capacity. Same procedure, same acceleration. The Avenger launched cleanly, climbing away with power to spare. For the first time, an escort carrier could launch its heavy strike aircraft with a full combat load. The Navy ordered immediate production. Morgan Smith's factories went into high gear. By early 1943, catapults designated H-4 and H-41 were rolling off the production line and being installed in escort carriers under construction across the United States. The Bogue-class carriers received them first. 45 ships in this class were built between 1942 and 1943, converted from partially completed merchant hulls. Then came the Casablanca class, the most numerous class of aircraft carriers ever built. 50 ships, all constructed at Henry Kaiser's Vancouver, Washington shipyard between November 1942 and July 1944. Nearly one per week, every single one of these escort carriers received a catapult. It wasn't optional, it was essential. Without the catapult, these ships would have been limited to ferry missions and light air patrol. With the catapult, they became combat platforms capable of hunting submarines, providing close air support for amphibious invasions, and yes, fighting off Japanese battleships when circumstances demanded it. The impact was immediate. Escort carriers deployed to the Atlantic began aggressive anti-submarine operations. Instead of waiting for U-boats to attack convoys, they formed hunter-killer groups. A single escort carrier with 4 or 5 destroyers would patrol areas where intelligence suggested U-boats were operating. The carrier would launch Avengers equipped with radar, depth charges, and acoustic homing torpedoes. These aircraft could cover enormous areas, forcing U-boats to stay submerged where they were slow and vulnerable to destroyer attack. The first combat deployment of the H-4 catapult came in March 1943, when USS Bogue deployed to the North Atlantic as part of a hunter-killer group. Her mission was to hunt German U-boats in the area between Greenland and Iceland, part of the dreaded mid-Atlantic gap where convoys had been most vulnerable to submarine attack. Commander Howard Avery commanded the Bogue's Air Group, Composite Squadron 9. He had 16 F-4F Wildcat fighters and 12 TBF Avenger torpedo bombers. The Avengers were his primary weapons. Each carried a radar that could detect surfaced submarines from up to 30 miles away, plus depth charges and acoustic torpedoes for the kill. Avery was skeptical about the catapult at first. He was a career naval aviator who had learned to fly from the big fleet carriers. The idea of being shot off a deck by a mechanical system rather than taking off under his own power didn't sit well. It felt like giving up control. His first catapult launch changed his mind. The Avenger was fully loaded, 9,200 pounds. Full fuel tanks, 4 depth charges in the bomb bay, and an acoustic torpedo slung underneath. Under normal circumstances, this aircraft couldn't take off from the Bogue's short deck, but Avery went through the pre-launch checklist. The holdback bar locked him in place. The catapult officer gave the signal, and suddenly he was accelerating down the deck faster than any takeoff roll he'd experienced. The sensation was strange. No gradual build-up of speed, just a massive shove that pressed him back into his seat. Then he was off the end of the deck and climbing, the Avenger's engine roaring, full control authority, flying speed achieved with 200 feet of deck to spare. When he landed back on the Bogue 2 hours later after a fruitless patrol, Avery found the catapult officer and shook his hand. "That," he said, "is going to change everything about how we operate." He was right. Within a week, Avery and his squadron had developed tactics that simply weren't possible before the catapult. They could launch heavily loaded Avengers in any weather conditions. They could get aircraft up quickly when a radar contact appeared. They could operate at full effectiveness, even when the ship was pitching and rolling in heavy seas. On May 22, 1943, the tactics paid off. An Avenger from VC-9 spotted U-569 on the surface about 80 miles from the Bogue. The submarine was recharging its batteries, unable to dive quickly. The Avenger attacked with depth charges, scoring a near miss that damaged the submarine's pressure hull. U-569 crash-dived, but she was leaking. The Bogue's escorts picked up the submarine on sonar and began a deliberate depth charge attack. For 2 hours, they pounded the area where the U-boat had dived. Finally, U-569 surfaced, her crew abandoning ship. The Bogue had her first kill. More followed. In June, VC-9 sank U-217. In August, they got U-525 and U-664. By the end of the year, the Bogue group had sunk 9 U-boats, more than any other single hunter-killer group in the Atlantic. The success was directly tied to the catapult. Without it, the Avengers couldn't have carried enough fuel and depth charges to patrol effectively. They would have had to choose between weapons and endurance. The catapult let them carry both, which meant they could find submarines and kill them. Other escort carrier groups matched or exceeded the Bogue's performance. USS Card sank 9 U-boats between June 1943 and June 1944. USS Guadalcanal sank 2 and captured U-505 intact. USS Croatan sank 2. USS Kor sank 6. USS Santee sank 3. The Germans noticed. In late 1943, Gross-Admiral Karl Dönitz, commander of the U-boat fleet, ordered his submarines to avoid areas where Allied escort carriers were operating. The risk was simply too high. A surfaced U-boat was vulnerable, and Allied aircraft could now reach areas that had previously been safe. The effect on the Battle of the Atlantic was dramatic. U-boat kills per convoy escort increased. Allied shipping losses decreased. By mid-1944, the Atlantic was effectively safe for Allied convoys. The U-boat threat hadn't been eliminated, but it had been reduced to a manageable level. Naval historians debate which factors were most important in winning the Battle of the Atlantic. The breaking of the Enigma code gave the Allies intelligence about U-boat positions. Improved radar lets aircraft and ships detect submarines. Better depth charges and acoustic torpedoes made attacks more effective. Long-range patrol aircraft closed the mid-Atlantic gap. All of these factors mattered, but the escort carriers provided mobile air coverage that could respond to intelligence in real time. When codebreakers discovered a U-boat patrol line, an escort carrier could steam to that area and launch aircraft to hunt them. The catapult made this possible by letting those aircraft carry the fuel and weapons they needed. Between 1943 and 1945, escort carrier-based aircraft sank 53 German U-boats. That's more submarines than were sunk by the entire surface fleet in some periods of the war. The USS Card alone accounted for 9 U-boat kills. The USS Guadalcanal captured U-505 intact after her aircraft and escorts forced it to surface, the only time the US Navy captured an enemy warship at sea since the War of 1812. None of this would have been possible without the catapult. The Avengers hunting U-boats needed to carry their full load of depth charges and acoustic torpedoes. They needed full fuel tanks to patrol for hours. Before the catapult, they would have had to choose between weapons and fuel. After the catapult, they could carry both. In the Pacific theater, escort carriers faced different challenges. The Japanese had fewer submarines than the Germans, so anti-submarine warfare was less critical. Instead, escort carriers provided air support for amphibious operations. This meant launching strikes against shore targets, providing combat air patrol over the invasion fleet, and spotting for naval gunfire. The first major test came in November 1943 during the invasion of the Gilbert Islands. 4 escort carriers, USS Nassau, USS Coral Sea, USS Corregidor, and USS Liscombe Bay, provided air support for the landings on Tarawa and Makin. Their aircraft bombed Japanese positions, strafed enemy troops, and provided close air support for the Marines fighting ashore. The catapults proved essential. The carriers were operating close to shore, which meant they were vulnerable to Japanese air attack. They needed to keep their decks clear of parked aircraft so they could launch combat air patrol quickly if enemy bombers appeared. The catapult let them launch fighters with full fuel and ammunition loads in minutes rather than tens of minutes. Tragically, the Liscombe Bay was torpedoed by Japanese submarine I-175 on November 24. The torpedo hit near the bomb magazine, causing a catastrophic explosion that sank the ship in 23 minutes. 644 men died, including Rear Admiral Henry Mullinix. It was the single greatest loss of life from an escort carrier during the war. The loss of Liscombe Bay didn't slow the escort carrier program. If anything, it reinforced the need for more of these ships. The invasion of the Marshall Islands in January and February 1944 employed 8 escort carriers. The invasion of the Mariana Islands in June used 18. By the time of the Philippines invasion in October, there were over 24 escort carriers operating in the Pacific. Each amphibious operation refined the tactics. carrier air groups learned to coordinate with shore fire control parties. They developed communication procedures for directing close air support strikes. They figured out how to maintain continuous air coverage with multiple carriers rotating their launches. The catapult made all of this possible. The ability to launch fully loaded aircraft quickly meant carriers could respond to requests for air support within minutes. A Marine unit pinned down by Japanese machine guns could call for air support and have Wildcats overhead firing rockets within 15 minutes. That responsiveness saved lives and won battles. The Escort carrier crews took pride in their ships despite the harsh nicknames. Combustible, vulnerable, and expendable was the unofficial meaning of CVE. The ships had thin armor, carried enormous amounts of aviation fuel and ammunition, and were slow enough that they couldn't run from trouble. But they could fight, and their crews knew it. Pilots who flew from escort carriers developed a respect for these ships that their fleet carrier counterparts sometimes didn't understand. Yes, the escort carriers were smaller and slower. Yes, they had shorter decks and less room for error on landing, but they were also more intimate. The crew was smaller, about 900 men compared to 3,000 on a fleet carrier. You knew people. The air group knew the deck crews personally. The catapult officer knew every pilot by name. This created a different culture. Fleet carriers were like cities, impersonal and bureaucratic. Escort carriers were like small towns where everyone looked out for each other. When a pilot didn't come back from a mission, the entire ship felt it. When a catapult crew managed an especially fast turnaround between launches, the whole air group knew and appreciated it. The technical excellence of the H-4 catapult contributed to this culture. The deck crews trusted the system because it worked. Pilots trusted it because it got them airborne safely every time. In 14 months of operations, the USS Card made 1,417 catapult launches. Not one aircraft was lost due to catapult failure. That kind of reliability built confidence. Other escort carriers had similar records. The USS Guadalcanal made over 1,000 launches during her hunter-killer deployments. The USS Santee made more than 800. The USS Bogue made over 1,200. Launch after launch after launch, the catapult system performed exactly as designed. There were close calls, of course. Hydraulic leaks, broken cables that had to be replaced, valves that stuck and required manual intervention. But the system was designed with redundancy and safety margins that prevented these problems from becoming catastrophic failures. When something broke, the crews could fix it quickly because the design was fundamentally sound. The S. Morgan Smith engineering team received regular feedback from the fleet. When problems appeared, field reports would come back describing exactly what had failed and under what conditions. The engineering team would analyze these reports, determine root causes, and issue technical bulletins with recommended fixes or modifications. This iterative improvement process made the catapult better over time. Early problems with seal wear in cold weather led to improved seal materials. Issues with cable fatigue in certain installations led to revised maintenance schedules. Each generation of escort carrier benefited from lessons learned on earlier ships. By late 1944, the H-4 catapult was a mature technology. The bugs had been worked out. The maintenance procedures were well established. The operating crews knew the system inside and out. It had gone from experimental equipment to standard, reliable, trusted technology in less than 2 years. This evolution from experimental to standard is how engineering progress actually happens. It's not one brilliant breakthrough. It's hundreds of small improvements. It's identifying problems and fixing them. It's learning from failures and incorporating those lessons into the next design. It's the unglamorous, patient work of making something better day by day. The engineers at S. Morgan Smith never became famous for this work. They went home each night to families who probably didn't fully understand what their husbands and fathers did at work. They read newspaper accounts of carrier battles in the Pacific and maybe felt a quiet satisfaction knowing their design was there, doing its job. But they didn't seek recognition. They had work to do. By the time of the Philippines invasion in October 1944, escort carrier operations had become routine. The ships knew their role: launch air support for the invasion forces, maintain combat air patrol, provide anti-submarine protection. These were well-practiced missions that the carriers and their crews had performed dozens of times. Task Unit 3, Taffy 3, was one of 3 escort carrier groups supporting the later landings. Commanded by Rear Admiral Clifton Sprague, the unit consisted of 6 Casablanca-class escort carriers plus escorts. The carriers were USS Fanshawe Bay, USS St. Lo, USS White Plains, USS Kalinin Bay, USS Kitkun Bay, and USS Gambia Bay. They operated about 70 miles off the east coast of Samar Island, far enough from shore to be safe from land-based artillery, close enough to provide rapid air support. The crews had been at it for several days, launching strikes against Japanese positions, running anti-submarine patrols. The work was exhausting, but not particularly dangerous. The big naval battle was happening elsewhere. Admiral Halsey's powerful Third Fleet, with its fast carriers and battleships, was engaging the main Japanese carrier force to the north. At least, that's what everyone thought. What Taffy 3 didn't know was that Admiral Halsey had taken the bait. The Japanese carriers to the north were decoys, carrying few aircraft and serving mainly to lure the American fleet away from Leyte Gulf. While Halsey chased them, the real threat, Vice Admiral Kurita's center force, was approaching from the west through the San Bernardino Strait. The center force was formidable: the super battleship Yamato, with her 18-inch guns, 3 more battleships including Nagato, Kongo, and Haruna. Heavy cruisers. 2 light cruisers. 11 destroyers. This was the most powerful surface fleet Japan had left, and it was bearing down on an invasion force protected only by escort carriers. Nobody in Taffy 3 knew this until Ensign Jensen spotted the Japanese fleet at dawn on October 25th. The first indication was anti-aircraft fire. Jensen was flying a routine patrol sweep when shells started exploding around his Avenger. He banked away and saw them. Ships. Lots of ships. Big ships. The distinctive pagoda masts of Japanese battleships. He radioed the sighting report. 4 battleships, 7 cruisers, multiple destroyers, distance 20 miles, course southeast, speed 30 knots. They were heading straight for Taffy 3 at maximum speed. Admiral Sprague's reaction, according to witnesses, was a mixture of disbelief and instant calculation. This couldn't be happening. The Japanese fleet was supposed to be far to the north being engaged by Halsey's carriers, but it was happening. Those were Japanese battleships on the horizon, and his escort carriers had maybe 30 minutes before those ships closed to gun range. His orders came quickly: all carriers turn south and run, make maximum speed, generate smoke, launch all aircraft immediately with whatever weapons they have, get them in the air and attacking the Japanese fleet, and send a distress call to every American unit in the Pacific. The catapult officers on all 6 carriers received the same order almost simultaneously: launch everything, now. Don't wait for perfect weapons loads. Don't wait for ideal spacing between aircraft. Just get them up. On the Kitkun Bay, catapult officer Lieutenant James Matthews had been preparing for routine morning operations when the order came through. He had 2 Avengers spotted on the catapult, both loaded for anti-submarine patrol. Depth charges, not the armor-piercing bombs you'd want for attacking battleships, but it didn't matter. Launch them anyway. First Avenger was hooked up and ready. Matthews checked the pressure gauge. 1500 psi. Good. He signaled the pilot. Engine to full power. Holdback bar engaged. Build pressure. The pilot gave the ready signal. Matthews dropped his flag. The catapult fired. The Avenger shot down the deck, reached the end, and climbed away. Matthews didn't watch it go. He was already signaling the deck crew to hook up the second aircraft. 30 seconds later, the second Avenger launched. More aircraft were coming up the elevator from the hangar deck. Wildcats. More Avengers. The deck crew worked in organized chaos, positioning each aircraft, hooking up the catapult bridle, checking that everything was secure. Launch, retract shuttle, next aircraft. Over and over. Matthews had trained for this. Every catapult officer had. But training scenarios assumed calm conditions. Time to do things right. This was different. The ship was heeling into a hard turn. Smoke from the smoke generators was blowing across the deck. And somewhere to the north, Japanese battleships were getting closer. The third aircraft launched. The fourth. Matthews could hear gunfire now, the distinctive boom of heavy naval rifles. The Japanese had opened fire at extreme range. The shells were falling short, but they were getting closer. Geysers of water erupted 1,000 yards to starboard, then 500 yards, then close enough that spray came over the deck. Fifth aircraft away, sixth. The catapult was running hot. The hydraulic fluid temperature was climbing. That was expected under rapid operations. As long as it stayed below the red line, they could keep going. Matthews glanced at the temperature gauge between launches. Still in the green. Barely. Seventh aircraft. This one was a Wildcat with nothing but machine gun ammunition. The pilot looked grim. He knew he was flying a fighter with pea shooters against battleships with 18-inch guns. But he took the catapult shot and climbed away to join the catapult ships. Others. Eighth aircraft. Ninth. The deck was almost clear now. Just 2 more Avengers in the hangar, being brought up on the elevator. Matthews could feel the ship shuddering from near misses. A shell landed close enough that the concussion rattled his teeth. Water cascaded over the deck. The deck crew kept working. 10th aircraft hooked up. An Avenger with a torpedo. Finally, something that could actually hurt a battleship. The pilot gave the ready signal. Matthews launched him. The Avenger climbed away and turned north toward the Japanese fleet. Last aircraft. Another Avenger, this one with bombs. The elevator brought it up. The deck crew rushed it into position. Hook up the bridle, check the holdback, build pressure, launch. 13 minutes had passed since the order to launch. The Kitkun Bay had put 11 aircraft into the air. Every single one had launched via catapult. Without the catapult system, maybe half of them would have gotten airborne, and they would have carried reduced loads. With the catapult, every aircraft launched with whatever weapons it had been loaded with, ready to fight. The same scene played out on all 6 carriers. The Fanshawe Bay got her aircraft up in 14 minutes. The St. Lo took 15 minutes. The White Plains managed 12. The Kalinin Bay and Gambia Bay both took about 16 minutes. By 7:15, barely 25 minutes after the Japanese fleet was spotted, over 70 aircraft were in the air heading toward the enemy. The Japanese fleet commanders were confused by the intensity of the air response. Their intelligence had told them these were escort carriers with limited aircraft complements and slow launch rates. But the sky was filled with American planes. Where were they all coming from? What the Japanese didn't understand was that the catapult had changed the fundamental equation of escort carrier operations. Pre-war assumptions about launch rates were based on conventional deck takeoffs. Those assumptions were obsolete. The new reality was that a Casablanca-class carrier could empty its deck in 15 to 20 minutes under combat conditions. 6 carriers could put 70 to 80 aircraft in the air in that same time frame. Admiral Sprague's carriers turned south and began generating smoke. Destroyers laid down chemical smoke screens to hide the vulnerable flat tops. But smoke doesn't stop 18-inch shells. The Japanese battleship Yamato opened fire at 7:04. Her massive guns sent shells weighing nearly 3,000 pounds toward the American formation. The first salvo landed short. The second straddled the USS White Plains. The third hit nothing, but the psychological effect was devastating. The escort carriers were being shot at by the most powerful battleship ever built. They had 5-inch guns for self-defense, 5-inch, against 18-inch. It was like bringing a pistol to a howitzer fight. But the carriers had one advantage the Japanese hadn't counted on. They could launch aircraft faster than anyone thought possible. The aircraft attacked in waves. The first wave, launched immediately with whatever weapons were loaded, hit the Japanese fleet around 7:10. Wildcats strafed bridges and deck guns. Avengers with depth charges made attack runs, even though depth charges were nearly useless against surface ships. The goal was disruption, forcing the Japanese ships to maneuver, breaking up their formation, buying time for the carriers to run. Meanwhile, the second wave was forming up. These were aircraft from Taffy 1 and Taffy 2, the other escort carrier groups to the south. They'd heard the distress call and launched everything they had. These aircraft had time to arm properly: torpedoes, armor-piercing bombs. They arrived over the battle around 7:45 and began coordinated attacks. A TBM Avenger from USS Natoma Bay made a torpedo run on the heavy cruiser Suzuya. The torpedo hit amidships, flooding the engine room. Suzuya lost power and fell out of formation. A Wildcat from USS Manila Bay strafed the bridge of Cruiser Tone, killing several officers and wounding the captain. Two Avengers from USS Kadashan Bay attacked the battleship Congo, scoring bomb hits on the superstructure. None of these attacks were sinking ships. The ordnance was too light, but they were inflicting damage, and, more importantly, they were everywhere. Every Japanese ship was under constant air attack. Captains had to choose between maintaining formation and taking evasive action. Anti-aircraft crews were fully engaged. The careful coordination Kurita had planned was falling apart. The Japanese cruiser Suzuya took multiple bomb hits. The cruiser Kumano had her bow blown off by a torpedo. The battleship Congo was straddled so many times by bomb hits that her captain started taking evasive action. The constant air attacks weren't sinking the Japanese ships. Most of the ordnance being dropped was too light for that, but they were disrupting the formation, forcing ships to maneuver independently, preventing Kurita from concentrating his fire. And then the other escort carrier groups got involved. Taffy 1 and Taffy 2, positioned south of Taffy 3, began launching their own aircraft. These groups weren't under direct attack. They had time to arm their planes properly with armor-piercing bombs and torpedoes. Their aircraft arrived over the battle area around 7:45 and began making coordinated attacks. The sheer weight of aircraft in the sky started to overwhelm Japanese anti-aircraft defenses. Every cruiser and destroyer had to maneuver constantly to avoid bomb and torpedo attacks. Every battleship had to split its attention between the surface targets it was trying to hit and the aircraft diving on it from above. The Japanese fleet's cohesion began to fracture. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 9/11, Vice Admiral Kurita made the decision to break off. He ordered his fleet to withdraw. He'd lost 3 heavy cruisers to combined air and surface attack. His remaining ships were damaged, and he was convinced, based on the intensity of the air attacks, that he must be facing fleet carriers, not escort carriers. Fleet carriers meant the big American task force was nearby. If he continued, he might find himself trapped between the American carriers to the south and Admiral Halsey's returning fleet from the north. Better to withdraw while he still could. Kurita's decision to withdraw remains controversial among military historians. He had the firepower to annihilate Taffy 3. He was less than 30 miles from the American landing beaches at Leyte, where he could have caused catastrophic damage. But the intensity of the air attacks, the volume of aircraft coming at his fleet, convinced him he was facing a much more powerful force than actually existed. The escort carriers of Taffy 3 had bluffed the most powerful surface fleet Japan had left into retreating, and they'd done it with the help of a catapult system that the Navy's own experts had initially considered unnecessary for these ships. The decision was made possible by the air attacks, and those air attacks were made possible by the catapults that let escort carriers launch their aircraft quickly, with full weapons loads. Without the catapults, the first American aircraft wouldn't have arrived over the Japanese fleet until around 7:30 or later. They would have been carrying reduced loads, the attack intensity would have been much lower, and Kurita might have pressed his attack long enough to annihilate Taffy 3. After the battle, the deck crews and catapult officers received little public recognition. The newspapers wrote about the heroic pilots making attack runs against impossible odds. They wrote about the destroyer escorts charging, battleships with torpedoes. They wrote about Admiral Sprague's tactical decisions. Nobody wrote about Lieutenant Matthews and his catapult crew getting 11 aircraft into the air in 13 minutes while under fire from battleships. Nobody mentioned the careful maintenance that kept the catapult working through 1,500 previous launches. Nobody talked about the engineering decisions made in Pennsylvania 2 years earlier that had made the whole thing possible. This is typical of how engineering contributions are remembered. The dramatic moments get attention. The enabling technologies that make those moments possible get footnoted, if they're mentioned at all. But the Navy knew. In after-action reports, carrier captains specifically mentioned the catapult performance. They noted launch times, number of aircraft put into the air, the reliability of the system under combat conditions. These reports went back to the Bureau of Aeronautics, where analysts studied them and incorporated the lessons learned into specifications for future systems. The data was clear. The H-4 catapult had proven itself under the worst possible circumstances. It worked in heavy seas. It worked while the ship was under fire. It worked when maintenance schedules had been compressed by weeks of continuous operations. It was exactly what the Navy needed. Production continued through early 1945 as the last escort carriers were completed. By war's end, over 120 H-4 and H-4-1 catapults had been installed in American escort carriers. The system had become standardized to the point that replacement parts were interchangeable between ships. A catapult that developed a problem could be repaired with parts from supply depots anywhere in the Pacific. This standardization was itself an achievement. In a rush wartime program, there's often a temptation to modify designs as you go, incorporating improvements but creating logistics headaches. The S. Morgan Smith team resisted this temptation. Once they had a design that worked, they stuck with it. Minor improvements were incorporated only when they didn't affect interchangeability. The result was a logistics system that actually worked. The S. Morgan Smith Company received the Army-Navy E Award in August 1944, just 2 months before the Battle of Samar. The E stood for Excellence in Production, the highest honor the government gave to industrial manufacturers during the war. When Rear Admiral Ramsey presented the award, he specifically highlighted the catapult system. He read a telegram from the USS Card, one of the Atlantic escort carriers that had been hunting U-boats. Our catapult equipment is plenty okay. Regardless of how the ship pitched, it got us into the air safely. A total of 1,417 launchings were made from the Card's catapult without a major repair. 1,417 launches, not a single major failure. This was the definition of reliability under combat conditions. The engineering team that had designed the catapult never received individual recognition. In wartime, security concerns meant that specific engineers weren't named in public documents. The company got the award, the workers got the recognition. But the brilliant individual or small team who solved the fundamental problems, who figured out the exact combination of hydraulic pressure, valve timing, cable strength, and metallurgy that made the system work, remained anonymous. This was typical of World War II engineering. Thousands of vital innovations were created by men and women whose names never made it into the history books. They did the work because it needed doing. They solved impossible problems because the alternative was failure, and failure meant American lives lost. The H-4 catapult was one of hundreds of such innovations, not glamorous, not the kind of technology that wins wars in dramatic fashion, but absolutely essential. Without it, escort carriers would have been marginally useful at best. With it, they became weapons that changed the course of the naval war. The post-war years saw dramatic changes in naval aviation. Jet aircraft were coming. These planes were faster and heavier than the prop-driven aircraft of World War II. They needed more powerful catapults to launch. The hydraulic-pneumatic system had reached the limits of what it could do. Something more powerful was needed. The British developed the steam catapult, and the US Navy adopted it in the early 1950s. But the transition didn't happen overnight. Through the late 40s and early 50s, H-4 catapults continued operating on escort carriers that were still in service. Some of these ships were converted for helicopter operations, others were used for training. A few served into the Korean War, providing air support for ground operations. The last H-4 catapult was probably decommissioned sometime in the mid-1950s. By then, the system was 15 years old, ancient by military standards. The ships that carried them were worn out, ready for the scrapyard. The catapults went with them. But the legacy persisted. The engineers who had worked on the H-4 took their knowledge to new projects. Some joined the teams developing steam catapults. Others went to work on arresting gear systems, the cables and hydraulics that stop aircraft when they land. A few ended up in the emerging aerospace industry, applying their understanding of high-force mechanical systems to rocket launch equipment. The principles they'd learned designing the H-4 remained relevant. How to transfer massive forces quickly and safely. How to build systems that work reliably under extreme conditions. How to maintain complex machinery in operational environments. These weren't just catapult lessons. They were fundamental engineering lessons applicable to countless other problems. In the aerospace field, rocket launch systems faced similar challenges. You needed to hold a rocket down while the engines built thrust, then release it at exactly the right moment. You needed hydraulic systems that could handle enormous forces. You needed to make split-second decisions about whether conditions were safe to launch. Sound familiar? Several former S. Morgan Smith engineers ended up working on missile launch systems in the late 50s and 60s. They brought with them an understanding of hold-down systems, hydraulic controls, and launch sequencing that traced directly back to the H-4 catapult. The connection was never publicly acknowledged, but it was there. The same pattern appeared in other fields. Amusement park rides that used catapult-like launches to accelerate cars, industrial systems that needed to move heavy loads quickly, even automotive safety testing equipment that used hydraulic launchers to simulate crashes. The engineering principles were universal. This is how technical knowledge propagates through a society. Individual engineers move from project to project, carrying their expertise with them. They mentor younger engineers, passing on lessons learned. They publish papers in technical journals, documenting design approaches that worked. They serve on standards committees, incorporating proven methods into industry specifications. The H-4 catapult became part of this knowledge ecosystem. Most engineers who used its principles had never heard of the H-4 specifically. They learned the concepts from textbooks or professors or experienced colleagues. The specific origin didn't matter. What mattered was that the knowledge was solid, proven under real-world conditions, and available to anyone who needed it. This is the real legacy of wartime engineering, not the specific hardware, which eventually gets scrapped, but the knowledge gained, which persists and spreads and enables new innovations. The engineers who designed the H-4 contributed to a body of engineering knowledge that's still being used today, 80 years later, in systems they never imagined. Modern electromagnetic catapults on the Gerald R. Ford-class carriers use completely different technology, but they're solving the same fundamental problem. Launch heavy aircraft from short decks. Do it safely. Do it reliably. Do it thousands of times. The engineers working on those systems studied the history of previous catapults, including the H-4, to understand what worked and what didn't. They learned that reliability matters more than peak performance. The H-4 wasn't the most powerful catapult that could have been designed, but it was reliable enough to work thousands of times without major failures. That reliability is what made Escort carriers effective combat platforms. They learned that operator interface matters. The catapult had to be simple enough that a deck crew could operate it under combat conditions, in bad weather, with incomplete information. Complex systems fail. Simple systems, properly designed, keep working. They learned that maintenance has to be practical. A system that requires extensive maintenance after every use won't be maintained properly under operational conditions. The H-4 was designed so that routine maintenance could be performed by the ship's crew with standard tools. That kept it working. These lessons seem obvious in retrospect, but they had to be learned through experience. The H-4 catapult program provided that experience. Every launch was a test. Every problem that cropped up was a lesson. Every solution that worked became part of the knowledge base. The escort carriers themselves didn't last. Most were scrapped after the war. They'd been built quickly, using merchant ship hulls that were never meant for long service lives. By 1947, the majority had been sold for scrap. A few served into the 1950s, converted for helicopter operations or used as training ships. But none survived to become museum ships. This means the most numerous class of aircraft carrier ever built, the Casablanca class with its 50 ships, has no survivors. Not one. You can visit the USS Yorktown in South Carolina, the USS Intrepid in New York, the USS Midway in San Diego, all fleet carriers preserved as museums. But you can't walk the deck of an escort carrier. They're all gone. The catapults are gone too. The last H-4 catapult was probably scrapped sometime in the 1950s when the final escort carriers were decommissioned. No museum kept one. No one thought to preserve this technology. It was obsolete by then, replaced by steam catapults that were more powerful and more efficient. But the impact of those catapults echoes through naval aviation history. The tactics developed by escort carrier crews, launching aircraft quickly under combat conditions, launching mixed strikes with fighters and bombers, coordinating attacks from multiple carriers, all of this became standard doctrine. The big fleet carriers in the 1950s and 60s used these same tactics, refined and improved but fundamentally based on what escort carrier crews figured out during the war. The anti-submarine warfare techniques developed by escort carriers in the Atlantic became the foundation for post-war ASW doctrine. The idea of a small carrier operating with a few destroyers, hunting submarines aggressively rather than waiting to be attacked, proved so effective that it influenced Cold War strategy for decades. The close air support missions flown by escort carriers in the Pacific, providing direct support to troops on the ground during amphibious operations, established procedures that are still used today. Modern Marine Corps aviation. The concept of a small carrier deploying near shore to provide continuous air support for ground operations, that's a direct descendant of what escort carriers did in World War II. And none of it would have worked without the catapult. The technical specifications sound modest now. Launch 9,500 pounds to 61 knots in 73 feet. Modern catapults can launch aircraft twice as heavy at much higher speeds. But in 1942, this was revolutionary. This was the difference between escort carriers being convoy escorts and being combat platforms. The battle off Samar is remembered as a victory of courage and determination, and it was. The destroyer escorts charged battleships with torpedoes. The pilots who made attack runs knowing they had no weapons that could actually harm their targets. The carrier captains who held their formations together under impossible circumstances. All of that deserves the recognition it receives, but it's worth remembering the engineers, the ones who designed the hydraulic systems that let those aircraft get airborne in the first place, the ones who tested prototypes until they broke and then redesigned them stronger, the ones who figured out how to make 9,500 pounds of steel and explosives accelerate from 0 to 70 miles per hour in 2 seconds without tearing itself apart. Those engineers didn't wear uniforms. They didn't receive medals. Their names aren't in the history books. But their work saved lives and changed battles, and proved that sometimes the most important innovations aren't the ones people notice. They're the ones that just work, quietly, reliably, thousands of times under the worst possible conditions. The chief engineer at S, Morgan Smith, whoever he was, probably went back to designing water turbines after the war. Maybe he stayed with the company. Maybe he moved on to other projects. We don't know. His personnel file would have been routine. Just another engineer doing his job. Nothing special to record. But on October 25, 1944, his catapult design helped 6 small carriers bluff the Japanese Navy into retreating from what should have been a massacre. That design let the USS Card make 1,417 launches hunting U-boats without a major mechanical failure. That design turned escort carriers from ferry boats into warships. The title asks about launching 28 planes in 8 minutes. The reality is more complex and more interesting. No escort carrier ever launched 28 aircraft in 8 minutes. They carried only about 24 to 28 aircraft total. But what they could do was launch their entire air group, fully armed and fueled, in about 20 to 25 minutes. As we covered earlier, without the catapult, this would have been impossible with combat loads. Engineering isn't always about making things faster or bigger or more powerful. Sometimes it's about making something work at all. The H-4 catapult didn't make escort carriers faster. It didn't give them better armor or bigger guns. It just made them functional. It turned a floating limitation into a weapons platform that won battles and saved lives. That's the real story. Not forbidden technology or revolutionary breakthroughs, just solid engineering, applied to a real problem by people who understood that lives depended on them getting it right. They got it right. The catapult worked. The escort carriers fought. And the war went on, one launch at a time. If this incredible story of forgotten engineering heroes moved you, please hit the like button, share it with fellow history enthusiasts, and subscribe for more untold stories from World War II that changed everything.